Hey Winston, Glenn Wellbrock with Verizon here to talk about CDC, automation in the network, the ROADM layer itself. Let's see where we're going to go.
Okay, great. Thank you for giving us some time to discuss about this interesting topic. We understand that Verizon has been the leader to deploy advanced ROADMs in the network. So could you tell us a little bit about what's the difference of ROADMs deployed today and ROADMs deployed like 10 years ago?
Sure. In fact, it's not even 10 years ago. We can look at just last year. Everything was in a fixed environment. You know, we called them reconfigurable, but they're only reconfigurable at intermediate points. The endpoints are still static, very static. You have a wavelength selectable switch or a blocker before that, but it was facing a direction, A, B, or C. And underneath that was a fixed port, usually an AWG or E-waveguide port or filter that said I could hook up a transmitter. Even though that transmitter's full band tunable, it has to be hooked to a particular port going a particular direction, and that's where it stays for the duration until somebody physically moves it. Again, on the receiving end, the receiver is wide band, but I had it hooked to port number 1, direction A, and that's where it remained for the entire duration of the service. Going forward with a colorless, directionless, contentionless, we have effectively a photonic fabric that allows us to put the transponder in and then determine later which direction and which wavelength we want it to go. And also if we want to move that at any point in time due to maintenance activity, or a cool one we call floating spare that I think we're going to talk about, is where we're able to move that on the fly. We can change the wavelength, we can change the direction, but we don't have to change the cabling. The cabling remains the same, and we also don't have to worry about blocking probability on that add-drop structure.
I see. So do you think that moving forward, everything will be automated by software?
Everything in our network.
Okay.
I mean, that's the whole goal.
Okay.
Previously, we did not have this agile photonic layer. It was very static, which meant it was nearly impossible to change after it was put into place. Now we're saying going forward, things like a floating spare. If that fiber, as an example, is no longer in use or no longer available, perhaps that's what's cut, that transmitter receiver is still there and it's still working. I could use it on another fiber to provide additional capacity until that fiber is fixed. When that fiber is fixed, I could move it back to that original fiber, again using the electrical fabric that's in the same network element to rearrange the traffic on a hitless fashion because it's got a bridge and roll capability. The photonic switch is always out of service. I mean, they're relatively slow, comparatively speaking. You don't have a bridge and roll capability at the photonic layer, but you do have the capability to manipulate that, where in the past that would have been an unusable asset while that fiber was broken, because you would have had to go out there and physically move it in order to take advantage of that same resource.
So we understand that CDC ROADM is the main vehicle for you to make this happen. Yeah. But CDC stands for colorless, directionless, and contentionless. Do you think that out of these 3 features, should carriers deploy networks with all 3 features, or they can say stay with only CD or only directionless? So what do you think the benefit is to have all 3 features included?
In a complex network design, keep in mind that perhaps enterprise networks could have a different view on this or something to that nature, but for a carrier, you've got a lot of nodes connected together. You know, metro networks are what we're building today. There's easily 100, 150, 200 of those ROADMs all connected together in a mesh environment. And you really do need the contentionless piece so that you don't have to worry about blocking, wavelength blocking on that add-drop structure. Because one thing to keep in mind is that the add-drop structure fills up 100%. The lines rarely do. The lines are, you know, generally 10, 20, 30% utilization on that fiber. Others perhaps higher, but on average it's quite low. Where the add-drop structure, the goal will always be 100% because they come in lower granularity, 8, 16, numbers like that, to where you really will fill it up. And you can go different fiber directions, as many as 16. So the probability of having or wanting to use 2 wavelengths of the same color going the same opposite directions is quite high on that add-drop structure, or at least we want to ensure that we don't have that limitation in the network going forward, because As you know, we have 4,000 or 5,000 ROADMs deployed today. When we look at the wavelength congestion on them, it does cause an issue after time, and we know that we're going to have to rearrange that network in order to get optimal utilization.
Mm-hmm. So why some of the carriers still kind of resistant to CDC and they only wanted to deploy CD today? And do you think they may have some issues in the future? And
I think it depends on how big that network's going to be, a big complex network. And I've heard the term many times, well, if your network is underutilized, you don't need it. Why did you spend the money? Well, the problem is you're going to need it later. You don't need it day one. It's day 2, day 3, day 4 when it really does come important. Future-proofing, because you know these networks don't change quickly. This is a 10-year endeavor to start deploying a photonic layer network. It's not the kind of thing that a carrier rotates out every couple of years. It is very a brownfield for a long period of time. You have to engineer it. You have to think out through what's this going to look like in 3 years, 5 years, 10 years when I'm getting ready to retire that asset. I want to make sure that I can use it at that time.
So all 3 functions will be needed for sure if the network is future-proof.
To make it future-proof in a complex environment where you've got a mesh design and you have many degrees that you're tying together, you're building express pipes, you're building local pipes that you want to move traffic around on, we feel that the modeling we did shows that it's well worth the investment of that contentionless.
What about the feature of gridless? Can you talk a little bit about it?
Yes, we've been using that even longer, and that's probably a great topic because a lot of folks said, why bother? 50 gigahertz is just fine. 100 gig works on it, no problems. You can even do 200 on it. And we agree, as long as the baud rate doesn't change. But as soon as we end up with a 16 QAM, the distance gets quite limited. The baud rate is what's going to change in another generation of equipment. That's what's going to allow us the better spectral efficiency, lower number of optical, electrical, the expensive parts on there. The way we can reduce that cost going forward and get higher data rates is through higher baud rates. Higher baud rates require more spectrum. Spectral efficiency on the fiber may not be dramatically different, but the cost of that devices in order to get that capacity will, and we want to take advantage of that. So that means going from 50 gigahertz, say, to 75 gigahertz as an example, or other increments. It doesn't have to be infinite, even though the devices are capable of very fine granularity or very fine tuning. I think we can standardize on a few. We asked for 25 gigahertz granularity. Of that, we'll probably only use 1 or 2 steps, depending on, again, what the baud rates are, in next generation equipment. Again, thinking out that network's going to be in place for 10 years. Existing networks started out as 10 gig, optimized for 10 gig. We eventually upgraded them to 40, and now we're doing 100 on those same existing 50 gigahertz runs. It's insane to think that we're not going to go above 100 on the next generation of equipment, or that we're not going to go above the current 28 gigabaud rates and get to higher baud rates. That's the normal progression of technology, and we believe it's going to be here sooner than some would think. And in order to take advantage of that, you really need to get the ROADM in place, because once you put the first wavelength on it, you can't change it. Or at least to change it, you have to knock down the entire fiber and that traffic and rearrange it. Forklift's a bad word in a telecom network. We're trying to avoid that, and it really comes at no cost premium for all practical purposes. That capability is inherent to the technology built into most wavelength selectable switches. Therefore, we want to make sure that we can take advantage of it.
I see. So essentially, Verizon's network is CDC plus gridless.
Correct.
That's really future-proof.
Future-proof, and it also doesn't have to look so far out in order to start realizing that value. That's the thing that some folks will say, well, if it's 5 years down the road, I don't care. I'll be replaced by then, or somebody else will have this job and I'll have to worry about it. This is something, the CDC structure, we take advantage of day one. What we do is day one, we'll put a transponder into the shelf. We don't have to predefine where it goes. And that is part of that CDC structure, or you could argue CD. Well, you put the second one in. A lot of folks start wavelength 1 on every direction, for whatever, just to make planning easier, or start a particular method of doing that. You're capable, or you're free to do that on a CDC structure day one. You don't have to say, well, I'm going to do wavelength 1 in that direction, wavelength 2 there, wavelength 3 here, because they're appearing on the same add-drop structure. Here we're saying, no, do what makes sense for the network design and remove that limitation of a contentionless environment at the add-drop structure. Same way with flexible grid. You know, the higher baud rates last week at OFC, most folks working on these transmitter receivers are talking a lot about higher baud rates. And the reason is trying to get more throughput on the same optoelectronics that are going to go into it. So we believe it's right around the corner, and that by the time we have this line system in place, we'll be able to take advantage of it.